I think we're going to continue today our discussion on Fisher and Schrock, or beams, because I think I had the feeling last week that we went very quickly. So, I mean, so we're going to slow things down a notch today, and these are the things that we're going to discuss. Something we haven't looked at is how to count, how to treat carbenes as ligands and how to count them in complexes, right? So, and how they affect the oxidation states. Now, we discussed this a little bit in the 2000 course, but we didn't really go into detail, and I wanted to understand it. And then we're going to revisit the Tebber reagent, which we looked at last week, but we went over very quickly. I want us to look at that again. And we're going to look at something called the pertussis reagent, which is very similar to the Tebber reagent, does the same thing. And then we're going to look at alkene metathesis, mechanistically. Okay, so that's the program for today. So let's start with how do we count carbenes as ligands? So, let's have a look at the situation. There's a classical Fischer carbene, and this is a classical Schrock type carbene. All right. The two cases, Fischer and Schrock. So how do we count this? How many does anybody want to venture a guess how many valence electrons there are in the Fischer carbene on the left? How many valence electrons on the complex?
Chromium was group
6.
6. So covalently 6 electrons, 2 from each carbon, so that's 10, 16, and 4 from...
No, I think it's 1.
Now that's the thing, it's a difficult business.
Exactly.
And there's a lot of people, advanced students, that also can't, believe it or not, count carbenes. They don't know how to count them. Now remember, there's two counting methodologies. There's covalent counting and there's ionic counting. Now, the easiest is covalent counting, so let's start with that. Now, if you count covalently, a carbene, irrespective of whether it's Fischer or Schrock type, is a 2-electron donor, like a carbonyl or phosphine. So in this case, it will be 6 times chromium is 6, 5 times carbonyl is 10, and 2 times the carbene is 2 is 18. So you count it as a 2-electron donor if you use the covalent counting methodology. Is everyone with me? All right. Same with Schrock. Same with Schrock. So how many valence electrons would that Schrock carbene have?
Which group was tantalum?
Tantalum is group 5. How many valence electrons? Count covalently. Tantalum is group 5. 10 valence electrons. So it's 1 times tantalum is 5, 3 times the alkyl group, which remember counts as 1, is 3, and 1 times the carbene is 2, is 10 valence electrons. You see, it's highly electron deficient. Now we can also count, that's the covalent counting. Now let's look at what happens if we count ionically. Or actually, let's do it under here. So if you count ionically, remember you have to take the oxidation state of the metal into consideration. Now that's difficult, right? Because it depends on whether it's Fischer or Schrock time. So let's start off with this. Well, the chromium, if it's a Fischer carbene, the carbene is a neutral ligand. It's a neutral ligand. So it's going to be 6 times chromium. Well, not 6 times chromium, I mean it's 1 times chromium, sorry. 1 times chromium is 6, 5 times CO is 10, and 2, so it's the same. 1 times carbene is 2 is 80. If the system is Schrock type and you count ionically, the carbene is counted as a 2 minus 4 electron donor. If it's Schrock type. Did everyone get that? So here, if it's Fischer type, it's a neutral 2 electron donor. If we're counting, well, irrespective if we're counting covalently or ionically, but here if we count ionically, it is a 2 minus 4 electron donor. So let's see what happens. Does anybody want to have try and count the electrons? Tantalum. We have to take the oxidation state into consideration. Here, the oxidation state of chromium is 0. What is the oxidation state of the tantalum in that complex?
Positive.
No.
So are the alcohols negative ligands?
Yes.
Oh,
So +5?
Plus 5. So how many d electrons?
None.
None. None. No electrons. How do we count the alkyls if we're counting ionically? If we count ionically, that counts as a 2 electron donor. So it's 3 times alkyl is 6. And how do we count the carbene? As a 4 electron donor, if we count ionically. So we get the same value. Now, notice, irrespective of whether you count covalently or ionically, you must obviously get the same result, right? The difficulty with counting ionically when dealing with carbenes is you don't know if it's Fischer or Schrock type. You see? You have to pick one or the other. But you get the same result. Notice if I counted this as a Fischer type carbene, I would have gotten the same result. It would have just been tantalum 3. Do you see that? In fact, let's do that. Let's count this ionically, assuming it's Fischer type, and see what happens. If it's Fischer type, the carbene is neutral. It's a neutral 2 electron donor. So what will the oxidation state of the tantalum then be? 3.
I don't get why there's such a difference between, like, one gives 4 and one gives 2, because the electronegativity of carbon is the same, right? So
Yes, yes, but in order to understand it, one has to look at the Dewar-Chat-Duncanson model. We'll look at that in a minute. All right. So 1 times tantalum is going, tantalum 3 in this case would be 3 valence electrons. 3 times alkyl is 6.
Tantalum 3 is 2, not 3,
6. And yeah, 1 times the carbene.
5 minus 3, so it's 2
This is 2, sorry, this is 2. And 1 times carbene is 2, so you get the same result, 10 valence electrons. So you see, the easiest is to count it, I guess, covalently. But I just wanted to show you this because if you count ionically, you can actually see the difference between a Fischer and a Schrock type and the effect that it has on the oxidation state. Remember, Schrock carbenes always go for maximum, they steal the electrons from the metal. Now, to come back to your question, why this difference? Why this difference? Well, the reason is that we can explain this in terms of the Dewar-Chat-Duncanson model. So here's a carbene, all right? And this is what a Fischer-type carbene can be represented as. Those are substituents. 2 electrons sitting in that orbital and a vacant p orbital here for a retrodative bonding from the metal. So here's the metal. So that would be a sigma donor. Remember, always put the phasors. And that would be a pi back bond. So that's the way to think about a carbene, or the bonding interaction between a carbene and a metal if it's Fischer type. Now, if you count the electrons there and you count the formal charge of the carbon, what do you get? 0. You see? If we just consider this fragment, is it a charged fragment? No, it's neutral, and it's a 2 electron donor. Now, if it's Schrock type, one way of thinking about it is that you have something like this. All right? So it steals all the electrons. Now remember what we're doing. The bond is formed with a metal and we're decomposing it into the two fragments. That's what the Dewar-Chat-Duncanson model essentially does, right? So this is basically what you would get. And this would, and so this, if you count the electrons, would be a, would be what? If you count the formal charge on the carbon, what do you get? 2 minus. 2 minus 4 electron donor. Now, let's not get confused. This is an important point. How I've represented it there is if we think about it counting ionically, right? If we think about it as if we decompose this fragment into a metal and a carbene using an ionic sort of framework like I did down here, right? But we can also think about it, and this is what confuses the hell out of everyone, in terms of the covalent framework. And if we think about, if we decompose a carbene, a metal carbene into these two fragments using the Dewar-Chat-Duncanson model, what would we get then? Well, what we would get is, for a Fisher-type system, it would be the same as in the ionic case. And what would it look like for, so you have metal, everything's the same. Sigma donor pi acceptor. And if it's Schrock type, it would look like this. Still a 2 electron donor, but notice what I've done now. I've decomposed that bond, that metal carbon double bond, into two, well, I've sort of done it in a covalent fashion. So those are the two possibilities to understand the bonding using the Dewar-Chat-Duncanson model. Are there any questions? Let's do another example of counting electrons, because I think this is a very important notion. So, I want you guys to be able to count this. You know, you have graduate students that can't do this. You even have some professors that can't do this, so don't feel bad. Let's take this. We looked at this complex last week and its synthesis. Does anyone remember how we made that? This rhenium carbene?
Is that through hydrogen elimination?
No. Using the diazo compound. Remember, we do photolysis, it's one of the routes. So does anybody want to count the electrons? Let's now just count it covalently. How would we do that? So, who wants to give it a go?
Which group is really a reason?
7. Yes, it's 18. Counting covalently. You see, if you count covalent, you don't bother about whether it's Fisher or Schrock type. It's much easier. All right, but let's just look at all the cases. So, rhenium, so we're now counting covalently. Rhenium is group 7, so that's 7 electrons. We have 2 carbonyls, that's 4 electrons. And we have 1 carbene, that's 2 electrons. And we have 1 CP, which is how many electrons? 5. We get 18 valence electrons. Does everyone see that? Now let's count ionically. Now what's the problem?
What's the type?
Hmm?
What's the type of carbene?
Exactly. Is it Fisher or Schrock type? Well, it turns out that this is one of those carbenes that's a little bit of both. So if you want to count covalently, you can assume it's Fisher type or Schrock type. You're going to get the same value anyway. So let's pretend it is a Fisher type system, all right? And we're now counting ionically. So it's now, what will the oxidation state of the rhenium be? 1, because the carbene is neutral and carbonyls are neutral, Cp is minus. So that's 6 electrons. 2 carbonyls is 4. 1 Cp, if you count ionically, is how many electrons? 6. And the carbene is how many? 2. We get the same value. You see that? Now let's count it, assuming that it is Schrock type. Let's count it as a Schrock carbene. So, how do we proceed? Yes, the oxidation state would be +3 because if we count it as a Schrock carbene, it's a 2 minus donor. So that's 4. Yes. 2 carbonyls, 4. 1 Cp, how many is that? 6. And 1 times carbene, how many? 4, exactly. Look at the Dewar-Chap-Duncanson model. We get 18. You see, the point is, irrespective of how you decide to count it, you should get the same value. You can count it Schrock type, you can count it Fischer type bionically. But you can also just count it, treat it as a normal ligand, and you can use the covalent counting methodology. Let's do one further example. Let us suppose what about this one? Yeah, for argument's sake. This is an iron carbene, a hypothetical one. Actually, I think this is this. Right. That's a carbene. So how are we going to proceed? Let's count it covalently. So, who wants to venture a guess?
Iron is group 8.
Group 8.
8, 10, 12, 14, 16, 18.
Everyone get that? So, iron is group 8. We have 4 carbonyls, that's 8, and 1 carbene. That's 2. Now let's count ionically, assuming it's Fischer type.
The carbene is still neutral. And the oxidation state is 0 on iron.
Correct.
So
It's the same. Now let's count it, which is not the case. This is incidentally Fischer type. Well, yes, it's clearly Fischer type because it's got a heteroatom. But let's just, for argument's sake, say we don't know and we want to count it as a Fischer type carbene. So what would the oxidation state of the iron then be?
Schrock type.
2. So we'd have, Josh, how many valence electrons? So if we count it Schrock,
Is it 2 minus?
so the carbene is a 4 electron donor if we count Schrock type ionically. 8, 6, 18. If we can do this, I'll be very happy because there's lots of people that can't do it. I'm serious. There's lots of people that can't do this. Even some professors that I know can't count carbenes. They don't know how to count them because they get confused between the covalent and the ionic counting methodologies, and they mix them up, and then it's a mess. So I would recommend that you stick to the covalent counting methodology because then you don't have to know if it's Fischer. It's much simpler. It's much simpler. All right. So that is about counting, and you, the nice thing, incidentally, about the ionic counting strategy is that you can see the effect that the carbene has on the oxidation state of the metal. Right? Okay. Now I want us to revisit a topic that we discussed at the end of last week's lecture, which is the so-called Tebe reagents. What do we use that for? Does anybody want to remind the class? Teba, Tebi reagent, Teba, Tebi, Teletubby, Teba. What is it used for? It's an olefination. I know it's early in the morning. I also had a late night. So, but you know, let's get some energy in here. How do we make it?
Where's the carbon now?
We take, let's revise, let's review this. I know this is difficult. We take titanosine dichloride, also called bis-cyclopentadienyl titanium dichloride, and we react that with what?
2 equivalents of aluminum trimethyl.
Correct. And what do we get? We get a very funky mechanism. And at the end of the story, we get this beautiful compound. That's it. That's the Teba reagent. Now, we looked at the mechanism last week. If you take the Teba reagent and you react it with a ketone or an aldehyde or an acid anhydride, any C double bond O functionality, and we get what? We get a 2 + 2 cycloaddition and transfer. Now, I said last week that this thing is in equilibrium with this. All right. Now, that's not strictly speaking correct. The equilibrium lies very, very far to the left. Very far to the left. To promote this equilibrium, in other words, to get access to this hot species here, which is the one that does the olefination, this is the one we want, we have to add a Lewis base. Like, for example, so let's just write here base. Who can give me an example of a nice Lewis base? Trimethylamine, triethylamine, trimethylphosphine, whatever, there's thousands. And what you get then is you get something like this. It's a base-stabilized carbene, essentially, that's generated. Now, if we take this species here, and we react it with, we looked at this mechanism last week, with acetone, what happens? Yes. We get 2 + 2 cycloaddition. Let's review the mechanism. So, let's review the mechanism over here. I want everyone to understand this. So let's not just forget about the base. Okay, we can put the base there, it's okay. So the point is the base promotes, does everyone understand that? Promotes the formation of this. You can think of the Teba reagent, this is the Teba reagent. You can think of it essentially as, let's say, the carbene, because that's a bridging carbene unit there, that has been trapped, that species has been trapped by the aluminium, and it stabilizes it. Now we add a base, the dimer dissociates, and we get this species here. All right, so we react this with acetone. Remember, this is the way that it goes. The oxygen goes that way, and the carbon goes that way. Why is that? 2 reasons. First of all, titanium is oxophilic, so it likes oxygen. Second of all, is that a Fisher or Schrock type system?
That's a shock type, yeah?
Absolutely Schrock type. As a colleague of mine says, as Schrocky as it gets. That's as Schrocky as it gets, right? Because I mean, we've got H's. Here, it's titanium. It's an early transition. It's got all the characteristics of a Schrock type system. So if it's Schrock type, is the carbon nucleophilic or electrophilic? Yes. So do you see why the acetone approaches in that way? Because, of course, this is an electrophile, remember? And this is a nucleophile. So now we get the 2 + 2 cycloaddition. and we form, the base is just sitting there, we form this. That's intermediate. Does everyone see that? And what happens now? Goes,
Goes again straight up.
goes again, goes again. So, boom, boom. Must really be comfortable pushing arrows. So we're going to get that plus the desired product, which is that.
Did the titanium complex exist as a dimer?
Yes, yes. So this doesn't exist as a monomer, this will then dimerize to form Cp2 titanium O2. Now, of course, a half molar equivalent if we check the stoichiometry. Now, what I want to point out about these 2 + 2 cycloaddition reactions is obviously they're in equilibrium. So this step here is in equilibrium. The second step, these can go backwards and forwards, backwards and forwards. So let's suppose we get here, it in principle can go back again, right? It can go back again. And so the forward direction we call a 2 + 2 cycloaddition. And if it goes the other way, we call it a cycloreversion. A cycloreversion. So the ring opens up again. 2 + 2 cycloaddition, 2 + 2 cycloreversion. All right, is everyone following? Any questions? Josh? Kunsulu?
Okay.
All right.
Was this the Wittig reagent on Wittig reaction on steroids?
Yes. This is a Wittig reagent on steroids because the Wittig reagent only works in selected